I hereby want to do some worked examples on structure and properties of matter. It involves various topics in that, so it's upon you to maybe select which ones fit what you'd want to find an example on. So welcome, and we'll want to begin from question 1. A gas cylinder has a volume of 0.04 cubic meters and contains air at a pressure of 2.0 megapascals. Assuming that the temperature remains constant, calculate the equivalent volume of air at atmospheric pressure at this value. So we are talking about volume changing, pressure changing. So we want to find the V2 in this case. So let's go to the question. We have pressure 1 given, volume 1 given, pressure 2 given, volume 2 needed. Okay. So now that we are talking about constant temperature, therefore this formula applies. You know, P1 V1 is equal to P2 V2 is equal to P3 V3 is equal to Pn Vn. Yeah. So that means when we make V2 the subject, we end up with P1 V1 over P2. Substitute values. P1 we know, V1 we know, P2 we know. Do the normal procedure for calculation. You will end up with 0.80 cubic meters as V2. Very simple. Question 2. A flask containing air is cocked when the atmospheric pressure is 750 millimeter mercury and the temperature is 17 degrees Celsius. The temperature of the flask is now raised gradually. So the temperature is raised gradually. The cork blows out when the pressure in the flask exceeds atmospheric pressure by 150 millimeters mercury. Calculate the temperature of the flask when this happens. Okay. So we are talking about a situation which changes because of changing temperature. Okay. So this is what we find. Since the volume is constant, P1 over T1 is equal to P2 over T2. What do we need? We need T2 because P1 is here, 750. T1 is here. We convert what we have, the 17 degrees Celsius, into Kelvin, which is now we are going to directly add 273 because of the normal constants. Yes, we do not want to go into the decimal part unless stated. So we have 290 Kelvin. Now P2 is atmospheric pressure plus the excess pressure that led to the blowing out. So we have this added. We have 750 plus. We are told the pressure exceeds the atmospheric pressure by 150. So you add that here, you end up with 900 millimeters mercury. So now that I have P2, I have T1 and P1, I can get T2. From this, make T2 the subject, so that will end up with P2 times T1 over P1 from this. So your T2 comes here, P1 gets there, and then this gets there. So you have this operated like this, to 900 times 290 over 750, which is equal to 261,000 over 750, and that is just 343 Kelvin. Back to degrees Celsius by subtracting 273, we end up with 75 degrees Celsius. As simple as that. Question 3. A cylinder of volume 2.0 times 10 raised to the power negative 3 cubic meters contains a gas at a pressure of 1.50 mega newtons per square meter. Okay. And a temperature of 300 Kelvin. Calculate the number of moles of the gas given in universal gas constant R is equal to 8.31 joules per mole per Kelvin. We are going to bring in the ideal gas equation. So that simply means we are going to use PV is equal to nRT, where N is the number of moles there. Do we have P? Yes. Do we have V? Yes. Do we have R? Yes. Do we have T? 300 Kelvin. So when that is the case, then just make N the subject. So N is basically PV over RT. When that is the case, just substitute values: 1.5 times 10 raised to the power 6 times 2.0 times 10 raised to the power negative 3 over 8.31 over 300, and this gives us 1.20 moles. Question 4. Calculate the root mean square speed of air molecules in a container in which the pressure is 1.0 times 10 raised to the power 5 pascals and the density of air is 1.3 kilogram cubic meter. So when you talk about root mean square speed of air molecules, we are taken back to ideal gas formula, and I think that is just what we normally operate with as this. This can be derived. I think I showed you how that is done, or you can find this from theory. This formula is what we are going to use. So when we talk about root mean square speed, is this part here, square root of this, okay, which is just this. Sometimes we find in the books written CRMS, okay, C subscript RMS. That's what we refer to this part. So this part can be obtained by rooting all the other sections, okay, which will give us C, because this is C squared bar, okay, but P is given, density is given. So from this formula we want to make C the subject. So you first multiply this 3 by this, you end up 3P divided by rho. Then when you have that, that is equal to C squared bar. So I want C alone, or C bar alone. You end up with rooting that and rooting this other part. So when you have C bar or C RMS, this actually equals to root of 3 times P, which is here, over rho, which is here. So when you have that, you will just root this answer and you end up with 480.38 meters per second. Now, now that we are working on this, they look very simple and very direct, and that is our objective. But let's imagine if you have the question alone without this answer, you'll have to really think of how to approach it. Yes. Question 5. Calculate the temperature at which the RMS speed of oxygen molecules is twice as great as the RMS speed at 27 degrees Celsius. So there's some ratio aspect here when we are bringing in the aspect of RMS speed of oxygen. Let's look at it. We are talking about calculate that temperature. So we want T1, okay? Let's say T2 is at this temperature here. So when you talk about T2 as 27 degrees Celsius, that is just approximately 300 Kelvin, because we're going to add 273 here, and it gives you 300 Kelvin. So let's say CRMS at T1. Yeah, theoretically we know if you take these ratios, CRMS at T1 over CRMS at T2 is actually equal to root of that temperature over root of this other temperature, theoretically. Okay, so let's look at that. But we have been told that twice CRMS at T2 is actually CRMS at T1. So in other words, instead of writing CRMS at T1, I want to write 2 CRMS T2. So when you write 2 CRMS T2 over CRMS at T2, this and this cancels, you end up with 2 here, which is equal to root of T1 over root of 300. So that simply means if you cross multiply, you have 2 root 300 is equal to root T1. Okay, so for you to get T1, you'll square everything, so that will be 4 times 300, which is 1200 Kelvin, or just 927 degrees Celsius, by subtracting 273 from there. Simple things, but very important. Question 6. A reservoir container is filled with geothermal liquid at 495 Kelvin and 102 atmospheres vapor pressure. Okay, we are talking about the concept of vapor pressure here. What will be the vapor pressure at 1023 Kelvin given the enthalpy of vaporization of geothermal liquid as 180.35 kilojoules per mole? and universal gas constant as 8.31 joules per mole per Kelvin. This is easy because we're simply going to use a formula which is in theory, and that formula is here. Okay, you see this? So our interest is to look from the question what part of this formula is given. Now P1 is actually this case here, 102 atmospheres. So that is what we have here. P2 is what we are finding, we are looking for. Okay, this is natural log. So this delta H vaporization is given here. Don't forget there is a kilojoule here. So that means we are going to multiply it by 10 raised to power 3. R is here, 8.31. T2 is actually this, 1023. T1 is 495. Okay, so just bring in those values. ln 102 over P2 is equal to all that value over 8.31. Then we have that multiplied by 1 over 1023 minus 1 over 495. If you operate this other part here, you'll end up with minus 22.62915. So in other words, you're simply saying that we have ln 102 over P2 is equal to minus this. So for us to remove the ln, or natural log, we are going to introduce exponentials. So if you introduce an exponential at this point, you end up with this value here. So if we say exponential ln this, we will end up with 102 over P2, which is here, and that should be equal to the exponential of this other part, which is this, minus 22.62915. So if I have this, then because this is just a value, P2 will just simply be 102 over the exponent of minus 22.62915. So this value is actually 6.8598 times 10 raised to power 11 atmosphere. High pressure, because actually we are talking about this great change in temperature corresponding to higher values of pressure. That is end of part 1. This is good news because you have a part 1 and there are other parts. So you can subscribe to get to other parts. Thank you.